Hi everyone, welcome back to my channel. I'm Coding Cosmo and this video is the second of my series C for Python programmers. In the first video we talked about the traditional Hello World example. Check it out in the description if you missed it. And in today's video we're going to talk about types. So types is a concept that you might already be familiar with because they exist in Python, although to me there's two major differences between types in Python and in C. First, in C, the compiler cares a lot more about types than Python does. What does it mean? It means that when you declare a variable, first you have to assign it a type. Whatever this unsigned char means, it's the type of this variable. And this type is for life. Like you cannot change the type of the variable and the compiler will throw errors at you if you're trying to do so. Secondly, in C, each type comes with a finite amount of memory associated to it. So that might make very little sense to you right now, but if we compare with Python, if you take a type like list, in a list by definition you can put as many stuff as you want. Your program can grow a list in an unbounded way, and there is no problem with that. Integers, they have this very nice property in Python that you can work and compute integers as big as needed. In C, it's not the case. Each type, and especially numerical types, they come with a limit. So in this car, for instance, that's giving you 1 byte, 8 bits of memory. So you cannot store information greater than a certain value. So we're going to see all that in details, but before you'll need this file misc.h, and the link is in the description. That will get you here, and from here just save it wherever your main.c file is. In the include preprocessing instruction, using quotes, it tells the compiler to fetch the file locally around your main.c file, whereas when you're using the angle bracket, the compiler already knows where to find those files. We are going to treat this file misc.h as a black box, and we are not going to try and understand its content, and just assume that it gives us this routine showBit, which is going to show us behind the curtains what is stored in memory in order to represent the variables and the types that we are going to use. And we're going to start by talking about this type, unsigned char. Okay, so unsigned char is arguably the most fundamental of all C types. And the reason why it's because in memory it uses exactly 1 byte, 8 bits, which is the smallest amount of memory that you can manipulate in C. And we're going to see that any other types only corresponds to a finite number of bytes. So unsigned char gives you 1 byte, and we're going to see that with our routine here. If we compile, we see that in memory, the memory content of our variable is written on 8 bits. We could have also had this information by using the operator sizeof in C. So you use it like that. If you do sizeof and of any variable, that will tell you the number of bytes which are used in memory to write this variable. So here it's 1 because we're using 1 byte. Okay, now in fact I've lied a bit because the fact that it's only 1 byte is encompassed only in the char. Now what does the unsigned mean? To answer that question we need like a few seconds of math, because we have the following question. On n bits I can represent 2 to the n different things. Okay, now it means that on 1 byte, which is 8 bits, I can represent 256 things. And the question that comes in mind is, what do I want to represent? And arguably the most natural thing to represent when you have 8 bits, it's all positive numbers between 0 and 255. So between 0 and 255 you have 256 things, and unsigned tells the compiler that this is the interpretation that we're going to get for our byte. And so that's a standard binary representation of 8-bit positive numbers, and there's a link in the description if you're not familiar with binary, but basically 8 zeros it's the number 0, 0, 1 it's 1, 1 0 it's 2, 1 1 it's 3, and each time you just add 1 in binary until you maxed out your capacity, which is when you have 8 ones in a row, which represent 255, which is the number 2 to the 8 minus 1. So immediately we have this question that comes in mind, and which is related to the concept of overflow. Is it, okay, but what if I try to exceed the capacity of an unsigned char? Here we see that we can only go up to 255, but what happens if I come and I start saying, okay, I want here 257. So if we compile, here we have a warning. So the compiler does not stop us, but it's smart enough to see that we are exceeding the capacity of our variable. And we see that in memory, we do not have 257. We just have what you can store of 257 on 8 bits. So we have the modulo 2 to the 8. Now, we had a warning because the compiler saw the value, like the value was hard-coded in the code, but that cannot happen, for instance, if you ask the user to give you the value. So you would do it like that, like with the function scanf. So you would do scanf, and here, esperluette ucarvar, and we are going to print the value. So now, if I compile this code, and I put again 257, but of course the compiler cannot say anything because the code is already compiled and this value is given by the user. But so the user gave me 257, but my program only retained 1. So this concept of overflow can be really dramatic to your code if you're not careful about it. So it means that when you're designing a C program, you need to be aware of like the maximum range that your variable can contain in order not to run in this problem where the user gave you a value, but yourself, you're storing something which is completely different. In the history of software, it has caused a huge number of bugs, for instance, in Bitcoin, because Bitcoin is written in C. Some people were able to steal money from some accounts by exploiting an overflow in different variables. So I put a link in the description if you want to check this out. So that looks very scary, but from the point of view of C, this fact that variables have a maximum capacity is a feature. Why? Because it allows you to be really parsimonious when you write your program in order to increase performance. Okay, now if we want to go beyond 1 byte, but there's types which are already there in C for this. If you want 2 bytes, you're going to ask for short. So here, let's put this back to 3. So short var, ushort var equals 3. If you want 4 bytes, you're going to ask for int. And just here, if we look at what is happening in memory, oops, sorry, forgot to. So we are always storing 3, but here on 1 byte, 2 bytes, 4 bytes. And these bytes here, they are equal 0. Because we don't need them to store 3, but they are here if we wanted to store bigger numbers. And we also get why I said that unsigned char was the mother of all types. It's because any type, really, in memory, it's just a succession of bytes. And it's really at a low level, like the address, the memory address of this byte is just before the memory address of this byte, just before the memory address of this byte, just before the memory address of this byte. When I said, here you see on my system that a char, it's 1 byte, a short, it's 2 bytes, an int, it's 4 bytes, but that could be completely different on your system. Not really completely, like a char will always be 1 byte, but for the rest, that could be different on your system because each system can choose this kind of parameters. Okay, and now if we go back to the math and just generalize, unsigned and bit integers, I'm talking about numbers between 0 and 2 to the n minus 1. So to give you an order of ideas, 2 to the 32 minus 1 is roughly 4 billions. So that's why int is kind of a type that people often use by default because it gives you some slack, like until you go to 4 billions, you can breathe a bit. But of course, exactly like in the example with 1 byte, you can overflow any of these types because it's a finite collection of bytes. And so if you try to store something which is too big for that type, for instance, 2 to the 64 plus 3, that won't be able to fit in an unsigned long, and so you'll get an overflow. We've talked about unsigned and bit integers, which are kind of the most natural thing to store on n bits. But what comes if you want to talk about negative numbers? They are called signed integers. So it comes with a cost. So because of the way they are represented, it's called binaries 2 complement, which is, by the way, a very beautiful way to represent negative number in binary. And I put in the description of the video a link to this concept. It comes with a cost because you are going to sacrifice half of the positive numbers that you were representing before. And it makes sense because on n bits, you can only represent 2 to the n things. So here we are cutting the apple in two, and instead of going to 2 to the n minus 1, we're going to go to 2 to the n minus 1 minus 1, and this half section that you saved, we're going to use it to represent negative numbers. And so in practice, for instance, you can take a char variable, so I will call it char var, and assign it to -1. By default, on most compiler, if you do not say unsigned, it's going to be signed. You can make sure by saying signed, but it's not necessary on most compiler. And if we print this variable, we're going to see that it's equal to what we want, which is -1. Okay, but now what happens if we look in memory to see what is stored for this value? So we see that the memory content of the variable is 8 ones in a row. Why? Because if you do +1, that's going to create only zeros. So you are storing the number such that x plus 1 equals 0, which is -1. Okay, but that can be really confusing because we've seen earlier another number with the same representation. It was the unsigned char variable, uchar var equals 255. So if we show the bits of uchar var, it's also a bunch of ones. So the only way the compiler can make the difference between 255 and -1 is if you tell the compiler whether it's unsigned or signed. And that can look not like a big thing, but again, it's prone to overflows, and overflows that are even nastier than the one we've seen before, because let's say you ask your user for a value like that, scanf esperluette carvar. So we'll talk more about the syntax in later videos. For at the moment, we don't really care. And let's see what's going to happen if the user says 255. Well, because we're using a char and not an unsigned char, it's going to answer -1. And that's tricky because the user gave a positive value and now we're dealing with a negative value. So this kind of overflows, they happen more often than we can think, and usually for beginners it's a real nightmare because you don't understand why you have negative numbers that appear. But if it happens to you, just go back to your types and make sure you've not overflown a signed type. Because if you overflow a signed type on the positive side, that's going to create negative numbers. So again, all what we've said, you can apply to types using more bytes, such that short, which is signed, int, which is signed, and long, which is signed. So when you're programming in C, it's good practice when you know that a variable can only be positive to signify it by saying it's unsigned. For instance, the size of a list or some stuff like that, it's always positive. And it will, tell everyone that's positive. Also, the compiler will know it's positive, so it's better for everyone. And also, you will be able to store bigger positive numbers. Like if you make the calculation from this formula, because we don't care anymore about all this chunk of negative numbers, when you say unsigned, you gain twice more positive numbers that you can represent. So you can store effectively bigger numbers, bigger positive numbers in an unsigned int compared to an int. Okay, so now we've covered non-negative integers, positive and negative integers, and what about the things that we usually learn next at school, which are real numbers? So of course, independently of C or Python, you cannot store a real number in a computer. Why? Because that would require an infinite amount of memory in general. If you take pi, you have an infinite amount of digits and you cannot store them. Okay, so what we're going to talk about are, by definition, an approximation of real numbers. So we have mainly two types for floating point numbers in C. Float var equals 3.14, and double var equals, you can use scientific notation, so 1.9 E10, meaning 1.9 times 10 to the 10. And so what's the difference between those two types? Again, it's a matter of memory. Double stands for double precision because it gives you twice more bytes to represent the data. So if we use our routine, we're going to see that the float variable is using 4 bytes to represent the data and the double 8 bytes. So we might wonder what's the link between the value 3.14 and this kind of random sequence of bytes. And the question is answered by an international standard, which is implemented on all computers, which is called IEEE 754, which explains how to relate this binary expression to a floating point number. I put a link in the description. A good rule of thumb is for you to use double each time you can. Why? Because that will minimize the number of precision errors that your code will run into. Especially if you're doing scientific computing, precision errors can be devastating, and a double, because you have more precision, will minimize this effect. Although it's not always possible to use double, especially if you interact with specialized hardware such as a GPU. It's often the case that GPUs will only allow you to work with floating numbers. So use double when you can, and when you can't, use float. Just out of curiosity, we're going to run the following experiment. We're going to take a float variable and assign it to 3, and take an int variable, because it's also using 4 bytes to represent data, in var, and also assign it to 3. And we're going to compare the memory content of those two variables. We're also going to print them, so f and %d for float var and int var. So what is going to happen? What we see is that both represent the value 3, but one with the standard binary representation of numbers, 1, 1, and the float variable with the representation which is very different looking, and again it's using this IEEE 754 standard. And here the point that I want to stress is that the only way the compiler knows how to interpret this abstract sequence of bytes, it's because we told the compiler what the type of the variable was. Thanks to this type assignation, the compiler is able to interpret an abstract sequence of data as being, in that case, the same number, 3, but written as a float on the one hand and as an integer on the other hand. It's also the occasion for me to talk about format specifiers. So you might have guessed by now, but what you need to put in scanf or printf next to the percent is dependent on the type. And there is a very good reference for that. It's a C data type Wikipedia page that's going to tell you for each type what is the format specifier you need to put into printf. For instance, we used unsigned char, and that's why I was using %HHU. It's because basically Wikipedia told me so. Okay, the last type that we're going to talk about is something which is really common in Python, but originally was not present in C, is the Boolean type. So it was introduced later in C, in a standard called C99, and you need this to include this file in order to use it, but the concept is pretty much the same. You have a bool var, and you can assign it to true, and if we look behind in memory what's happening, but since we've said that the smallest amount of memory that one can consider in C is a byte, we are still storing a byte, but the value can be only 0 or 1. And the logic is very simple, is that if you assign the variable, in fact, to anything different than 0, that's going to be equal to 1, so the truth value of 1. And the only way you can have something false is by saying bool var equals 0, or write the bool var equals false. That's the same thing. And the reason why it's like in Python, the reason why this concept of Boolean was not needed in earlier version of C, and in general in C it's not really needed. It's a good practice to use it, so you tell your user that something is a Boolean, but truly inside the machine, any value which is different than 0 is going to evaluate to true, and 0 is the only value which is going to evaluate to false. Okay, now the last concept that I would like to cover with you in this video is actually quite straightforward. It's the concept of const variable. So const int, you can use this keyword for any type. Here, for instance, int var equals 47, and it does what we want, which means that this works, no bother. But if you come and try to modify this variable, you're going to run into a compilation error. So it's a compiler which is going to see that and say, no, you cannot change this variable, it's read-only. So as a conclusion, we're going to go back at the beginning with kind of a naive question, is that why a byte, which is like a car var, is called, why this type is called car? And that's because historically characters were stored on 1 byte, and that's the Ascii table. Like if we say, for instance, equals to A, so note that there is a difference between single quotes and double quotes compared to Python. A single quote is only for 1 character and 1 Ascii character. And so if we look at that, if we print this character with %c, and let's look also at the value which is behind in memory. So we see it prints the character A and it says 97, and that's because if you look at the standard Ascii table, 97 is indeed the value that is standard for A. By the way, because the Ascii table is in order, it gives the following feature, which is kind of fun in C, that if you ask what is A plus 1, you'll get B. And so you don't have to play with ORD and CHR like functions in Python. When you want to manipulate characters, you can directly use standard arithmetic in order to move through the Ascii table. In summary, there are 2 main take-home messages to this video. 1, the content of any variable is encoded on a finite number of bytes. And 2, the only way the compiler can give a meaning, can interpret this sequence of bytes, is thanks to the types that you gave to the variable. For instance, we've seen that 8 1 in a row, like a byte full of ones, it will be interpreted as the number 255 if you chose unsigned car, and it will be interpreted as the number -1 if you choose car. So once you've understood those 2 seemingly simple statements and their consequences, for instance, we've talked about overflows, then you've actually understood a lot about memory in C, and this gives you solid foundations to learn more advanced concepts. Talking about more advanced concepts, it could seem from what I said that it's impossible in C to grow a list as big as you want or to work with integers as big as you want. But if it was not possible to do that in C, it would not be possible in Python, since the main Python interpreter is written in C. So yes, it's possible, but you cannot do that without the concept of pointers that we will cover in a few videos. So that's it for today. Thank you very much for watching. Next time we'll talk more about types, in particular composite types, which are the equivalent, the weak equivalent of Python classes in C. And if you have any question, please don't hesitate to put it in the comments. Don't forget to subscribe, and until next time, bye-bye.